Hi, I am Byun from ETRI Korea. Today, I'm going to present the Multi-Worker NFD, which is an NFD-compatible high-speed NDN forwarder, and demonstrate each performance test. This is a joint work with Jongseok, Myung, and Namseok from ETRI. The NFD is the default NDN forwarder in most NDN researches. It is designed for modularity and feature extensibility, but shows quite low forwarding performance. So we analyzed the NFD code and did performance profiling with Intel Byun profiler and identified that the main bottleneck of NFD performance is its single-threaded forwarding architecture. NFD only uses single core for forwarding, even in multi-core CPU systems. So we developed a high-speed NDN forwarder named Multi-Worker NFD. Multi-Worker NFD has multi-thread forwarding architecture. Its design goals are high-speed forwarding, full compatibility with the NFD and NDN applications, and supporting easy porting of any new NDN NFD features. High-speed forwarding is achieved with multiple forwarding workers. For full compatibility and each porting of a new NFD feature, we maintain NFD's forwarding plane architecture as is and support all the management features of NFD with the same API. It is based on NFD 0.7.0. Multi-Worker NFD has multiple input threads, multiple forwarding worker thread management, and arrive manager thread. Arrive manager thread is same to NFD, is unchanged. Each input thread receives packet from each associated faces and distribute to the forwarding workers based on hash of name prefix of pre-configured length. Actually, input thread stores the packet to a buffer and sends the packet buffer pointer and each input face ID to the selected forwarding worker using message queues. Forwarding worker do the all packet processing jobs starting from NDN link protocol handling and finally transmit the packet to the outgoing faces. Forwarding tables such as PIT, CS, FIB, measurement tables are distributed to the all workers, so each worker has only the associated table entries. The number of forwarding workers is configurable. Let's look inside of input thread in detail. One input thread is created for each physical port and launched on the configured core. All faces whose local endpoint is associated to an input port are registered to the I/O service of each input thread. For prefix matching between interest and data, all interest data having the same name prefix of pre-configured length are sent to the same forwarding worker. Another information used for packet distribution is the PIT token in the NDN IP header. Forwarding worker encodes the worker ID to the PIT token of transmitted interest. If the peer forwarder supports PIT token, the returned data or NAC has the token of matching interest, then it can be sent to the forwarding worker of matching interest without looking the name prefix. These schemes are adapted from NDN DPDK, which is another multi-thread NDN forwarder. We added a new distribution rule for fragmented large packets. As the first fragment has the name and PI token, the distribution rule is same to the interest and data. For subsequent fragments, input thread store the worker ID of first fragment with its fragment index, which is the identifier of a fragmented packet. Because the subsequent fragments has same fragment index, they can be sent to first fragment forwarding worker. The management thread is the main thread, and it launches input and forwarding worker threads on the configured cores. It receives and distributes packets from local application faces and internal face. It has all the management features of NFD handled by NFD commands and configuration file. Because the table and statistics are spread to the multiple threads, for the processing logic for each command should be modified and is under development. Today, we demonstrate the forwarding performance of MW-NFD with the NDN packet generator server and MW-NFD server. The servers are connected with two TANG ports. For test, we developed the NDN packet chain, which is based on the BDK packet chain 19.12. It can send a stream of interest with unique names and return data with same name to the received interest without NFD. This is the exact matching forwarding test, and interest aggregation and CS hit does not occur. MW-NFD server has the Xeon Gold 6242 CPU with 16 cores. FBI size is 10K, and next hops are set to send interest from port 0 to port 1, interest from port 1 to port 0. In this demo, we define the forwarding throughput as the sum of forwarded interest and data throughput. Left graph shows the PPS throughput for various data size when the number of forwarding workers is 10. Because MW-NFD allocates 2 additional cores for 2 input threads, this result came from 12 core computing powers. The right graph shows the bandwidth throughput with various number of forwarding workers. We can see that the throughput is saturated at 8 or 10 workers, which is 16.4 gigabps with 8K byte data. This saturation is due to the performance limit of the 2 input cores. If more physical ports are used and the server has the additional cores, the maximum throughput can be linearly increased proportional to the number of ports. In this demo, MW-NFD can yield about 13 times of NFD throughput. Until now, we have focused on the implementation of multi-thread forwarding architecture of MW-NFD. Our future work includes the management feature of developments interacting with multiple input and forwarding worker threads, and compatibility test with the existing NDN applications. After the compatibility test, we will release the source code of MW-NFD. In parallel, we will try to enhancing some NFD's forwarding logic implementations, such as packet receiving process in the input threads and CS operations. In this demo, we show the Multi-Worker NFD can yield more than 16 gigabps of throughput with 10 workers for 8K byte data. We added the MW-NFD section in the NFD configuration file. We assigned core 0 and 2 for input thread, and we assigned 10 forwarding cores. And the previous length of distribution is set to 2. And this is the packet chain configuration. The name stream size is 10 mega entry, and the data size is set to 8K byte. So we're learning the NDN packet chain and MW-NFD. Start sending the interest. You can see the CPU load of MW-NFD is about 1200%, and this means that the MW-NFD fully utilizes the 12 cores, 2 for input thread, 10 for the worker thread. And the port 0 and 1 is 10G, and this is the RX PPS of port 0 and 1 of packet chain, and the sum of the RX PPS is about 500K PPS. And this is in turn the PPS performance of MW-NFD. And this is the RxTX bandwidth of port 0 and 1, and sum of RX bandwidth is about 17 gigabps. This means that the bandwidth throughput of MW-NFD is 17 gigabps for 8K byte data. Thank you.